have discussed about the band, and we used the three models. One is chronic, penny, and then tight binding, approximation, and weak binding approximation. And in this weak binding approximation, we have E versus K diagram. We can create the E versus K diagram, and everything can be put into pi over A, and that is certain series of direct energy densities like this, and the outermost band, two things is of our interest, because the solid reacts with the valence electrons of the materials. So if you draw, you just neglect all the energy levels and low energy levels, and then the highest energy level that we have to consider is the uppermost two energy levels, which has been drawn from here, and then we call this valence band, and this is going to be called conduction band. And the low level energy densities is not going to react with external forces, so that we don't have to care about those low energy levels. The outmost energy levels is of our interest, and then the outermost band is going to be called the conduction band, and then the next nearest one is going to be called valence band, and then these two energy delta E is going to be called band gap of this material. Okay, so every reaction happens on this conduction band and valence band. Okay, in the textbook 124, page 124, there is four different ways of describing band properties, and the first one is a flat band diagram, which is flat band diagram, and that is the conduction band and the valence band, something like this. That is a flat band energy diagram. Okay, we just set the conduction band energies and the valence band energies, and then x. This is the x-axis. Okay. Of course, this is the energy levels. That is going to be called the flat band diagram. And in this case, if you draw this thing into a flat band diagram, maybe this is going to be the conduction band and the valence band, something like that. All right? And then another way to draw the energy levels is the EK diagram, which is this EK diagram. Okay? And that EK diagram is going to be, if you draw on the same scale of this, now in this case we have k-axis along this direction, and then y is the energy, and then the conduction band edge is going to be drawn something like this, and the valence band is going to draw something like this. And this is EK diagram corresponding to this flat band diagram. And another drawing for this is energy density versus energy diagram. And that is, if you draw this in terms of the y-axis is going to be now the available energy densities the electron can occupy. And then that is going to be distorted, and then square root of E, and E is proportional to square root of E at both end edges, something like that. So at the center of this each band is going to be distorted. It's away from the free electron model. And this is somewhat look like energy densities, available energy density versus E. So in real materials, we can distinguish metal and insulator and the semiconductor, right? And in metal case, this conduction band is partially filled with the electrons. So you can draw the electrons going to occupy something like this for the case for the metals. In the insulator case, we do not have this. It's just a field up to valence band. And then this is, of course, the band gap in this material. And the band gap is around more than 8 electron volts or something like that. In the semiconductor case, this band gap is around 1.2, less than 2 electrons. Less than 2 electron volts, and then we call that semiconductor. So this N versus E is also very useful to make a distinction among the materials. Okay, and then finally we have equal energy surfaces in K space. And then if you draw 2 dimension, 3 dimension, you have to go for the cubic thing, but this is the energy levels, and then this is a KY, and this is a KX, this is the wave number, so that it has X, Y, Z directions, and then we just pick up the 2-dimensional representation two-dimensional representation, and then we can draw this, the equal energy surfaces. And at the edge, at the corners, we have a free electron-like behaviors. And at the center, we also have free electron-like behaviors like this. Free electron-like behavior. Free electron-like behavior means in these corners and the center, energy is h bar square k square over 2m. Okay? That is the free electron kinetic energies. And then in equal energy surfaces, we can draw that E and K square thing, the circle, which corresponding to the free electron energies. So we have 4 different ways to describe the free electron energy states in a solid. Okay, most useful one is this EK diagram. We use the EK diagrams in most of the cases. Today we are going to discuss about the application of these EK diagrams to find material properties like electron velocity, free electron velocity, which is related to the free electron mobilities as well, and effective mass, and some physical properties related to the EK diagram. Before we go into that, I want to mention that at the bottom of the conduction band, we have a free electron-like behavior so that the energy can be described as h bar square k square over 2m. And also at top of the valence band, we also have a free electron-like behavior so that the energies in this case is going to be expressed as energy is going to be h bar square E k maximum k max minus k square over 2m, something like this. Okay, and if you make this effective mass, then at the bottom and top, something like this. We have to use the effective mass. And in equal energy surfaces, in these drawings, the simple cubic structure, simple cubic, is going to be represented as a cubic. Okay, but in FCC, it's going to be represented as a BCC, and then the BCC is going to be represented as the FCC. We have seen this in the X-ray diffraction patterns, right? The reciprocal lattice. Same thing happens in the equal energy surfaces, like what we are talking about is KY and the KX, for example, two-dimensional representation. This is going to be pi over A and minus pi over A and the minus pi over A as a first brilliant edges. And the three-dimensional representation has been given in the text, which is a figure 7.5. You just refer to it, okay? Now, free carrier properties. The first free electron velocities. We know the energy is going to be h bar square k square over 2m. And then round k, round E over round K, it's going to be h bar square K over M, right? We have to use the effective mass here. We're going to go for the effective mass later, but anyway. And so group velocity is going to be h bar K over M. Effective mass here. Sorry. Since now this is corresponding to the first derivative of that, so that the group velocity is just a slope in the EK diagram, right? What about the effective mass? The force is MA, and that is round T over round P over round T, and that is D or DT, and then we know H bar K, that is P, so that F now it's going to be H bar round T over round K. All right? And round T over velocity over round T, this is going to be the acceleration, right? That is A. And then we know the VG can be represented with this first derivative of E with respect to the K, so that we just put that into here. And then by the chain rule, we can set this something like this. And then that is going to be round k over round t, round square e over round k square. Right? So effective mass now is going to be F divided by acceleration, so that the F now is going to be h bar round k over round t, and acceleration is just this, right? Go to the nominator, and then that is going to be h bar d square e over dk square. So that is the effective mass. This is another expression is now going to be 1 over effective mass is going to be 1 over h bar square, and the second derivative of EK diagram. So effective mass is related to the second derivative of energy with respect to k, and the velocity is related to the first derivative of the curve, EK diagram. Now, for number 3, maybe we can talk about the mobilities, free electron mobilities. All right? Mobility by definition, mobility is group velocity divided by the electric field, right? That is the mobilities. Normalized velocity, we should say, okay? And this is a material constant. Material constant. Now, F equal to ma again, and then in the electric field, it can be set something like that, right? That is the force. And the momentum is a integration of force with respect to the scattering relaxation time. And that is going to be Q tower. Here, the tower is the relaxation time, between scattering. You can see in a solid, the free electron is moving around, but it just scatters with the host atoms and with another electrons, things like that. So that if you check the velocity of free electrons with respect to the time, then before scattering, it just accelerated with the time, and then by elastic scattering, it just goes to 0, and then go to be accelerated for the certain period of time between the scattering, and then after the scattering goes to 0. It's something like this, seesaw shaped. So when we say the velocity of free electrons in a solid, then it's just the average values we are talking about. This is the average values And then we call that is the velocity of a free electron in a solid. Okay? So between the scattering, we call this is the relaxation time. That relaxation time is different according to the materials and the material conditions like impurities, defects, and so grain boundaries and so forth. Okay, so that relaxation time is different from material to material. So that the mobility now becomes so the Q electric field tower here, the momentum is going to be mv, and then velocity is the multiple of mobility with electric field. So that the mobility now becomes something like this. If you look into this, it's very natural to see that the mobility of any particle, anything, any substance, is proportional to the weight, right? If it is heavy, it is going to move slow, right? And then the acceleration, if you scattering time is long, then it is going to be accelerated so that the mobility becomes large. So without any derivation, complicated derivation as shown here, it's not that complicated, but without any logical explanation, just by looking at this, we can see that the mobility is going to be inversely proportional to the effective mass, and then it's going to be proportional to the relaxation time between the scattering. Now, that is very natural to see that the mobility is going to be like this. And the same token, as far as the effective mass is concerned, what is effective mass? Why do we call effective mass? The effective is very interesting English. It's a very interesting word. We really don't know the mass, but it is corresponding to mass. Then we call that effective mass. So when you, for example, when you measure the mass of electron, it's so light, it is very difficult to measure 10 to minus 19 something, right? There's no tool in the world to measure that light substance. So when you talk about the electron, we usually say effective mass, because what we are doing to measure the mass of electrons, we just measure the force that the electron can feel, and then we variate the accelerations, okay? And then by the Newtonians, this thing has to have a straight line. It should. And then this slope is corresponding to mass. It has to. So this way we measure the mass, and then we call that effective mass. Okay? So when you have a valence band, for example, this is the valence band shape in the EK diagram, right? E versus K diagram. Let's draw a little bit precise. It should be 0 at this end, and the maximum, and then it should be 0 again. And then here, this is going to be pi over a and minus pi over a, right? And then this is 0. If you plot the velocity the first derivative of this is going to be the velocity, so that the velocity is going to look like this. And then this side, the velocity is going to be positive, and this side is the velocity is going to be negative. What does that mean? The negative velocity. It means that we push this way, but the electrons are moving toward us. That is the meaning, physical meaning of the minus. Okay? And then if you plot the effective mass, that is corresponding, that is related to the second derivative of this. So that now here we have positive mass, and then here we have negative mass, and then here again positive mass. This is the effective mass in the K diagram. Here once again the negative mass means the same thing as we described for the negative velocity. Negative mass just means that it reacts differently, okay? The opposite direction. You can do the same thing for the conduction band, and that has been given in the text. Like conduction band is going to look like this. And then you can create the velocity by first the derivative of this, and then effective mass by the second derivative of this, right? And that is given in the text. So with the EK diagram, we can have a velocity and effective mass response. This. Okay, one thing I should say, the effective mass basically we can obtain this effective mass by F and acceleration, and then slope. This is the effective mass. That's what I have told you. And what is the conduction band effective mass of electrons in the conduction band, and then effective mass of electrons in the valence band? Which one? Valence band. Which one is going to be big? The mass of a valence band is going to be big, right? Because valence band electron is filled, so it's just like a parking lot. All cars are fully booked, so that just if you have just one empty spot, then the way to move that cars inside this parking lot, you have to move one by one to move that space, right? That is just like the electron movement in the valence band, and we call that the hole, moving of a hole in the valence band in this case. Okay, then the electrons are moving in a conduction band. It's just the empty parking lot and moving one car moving around, and that must be very fast, right? So that the effective mass is going to be very small. We're talking about the mobility of electrons and mobility of holes. If you compare that, obviously the mobility of electrons is much faster than the hole, that of hole, right? And this mobility is related, proportional to the inversely proportional to the effective mass, so that we can see effective mass of the hole is much bigger than the electrons. Okay? So that in the EK diagrams, okay, EK diagrams, if you, this effective mass is related to the second derivative, the curvature of the EK diagram, so that when you draw the conduction band, you should very small curvatures in this case because of this effective mass. And then when you draw the valence band, usually it should be wide with the big curvatures. That is common practice in a solid. Okay? And today we are going to hand out you the new homework set. And in this class, we read moving fast. And then those homeworks is just for your understanding of the thing. So the homeworks, I'm sure that homework will help you to understand this, the contents of the class. Try to solve the homework, but do not complete the homework. Maybe sometimes it's difficult for you to just finish out. You don't have to get the 100% correct answers to the homework. Just try to enjoy the homework, okay? And then some of the homeworks you may get a solid idea what we are talking about. So it's just going to, the homework will help you. So don't think it is a burden. Okay, try to enjoy it. Okay.